All right, let's get started. So in case you guys wonder, yes, I did update the title. I thought it was missing a bit of attitude. Hopefully you find it better like that. So today I really want to show you all of the lessons, or most of the lessons we learned at Triple Quote while working on SBT and Scala tooling in general. So I'm really going we're really going to explore several concepts of SBT, trying to understand how it works. We're trying to build sort of an intuition of what SBT does and how it does things. And on the way, I'll show you a few utilities that I think they're extremely useful, and I feel and believe that most of us ignore they exist, and they're readily available at our fingertips. So armed with this knowledge, my hope is that you'll go back to your projects and you'll be able to analyze, inspect, and resolve inefficiencies that you may have in your build. But before we dive into SBT, let me just give you a little bit of background on why do I care so much about Scala projects build time. So some of you probably know me. I'm a co-founder of Triple Quote together with Julian Dragers. Back in 2016, we started Triple Quote with the goal of making Scala compilation fast. I guess it's no wonder why we started with that goal. So before Triple Quote, we were working at Lightband, and what we've been hearing over and over is that Scala compilation is slow. That's why I cannot adopt Scala in my project, in my team. It's a risk that I need to mitigate. And we were crazy enough to believe that we could do something about it. And that's how it all started. And that's why today we have Triple Quote Hydra. So this is our commercial Scala compiler, multi-core Scala compiler. So we like to think about it as our friendly multi-headed monster or drone. And speed-ups with Scala are actually quite interesting. In fact, John asked me to give a talk about Scala, about Hydra, but I thought there wasn't much more to say other than it works great, and you guys should just go and try it out. It's very easy. You can try it out from SBT, from IntelliJ, from Gradle, from Maven, and it works great. I mean, you get our customers report speed-ups from 2 to 7 times faster Scala compilation. And this is with common hardware, usually a laptop or a laptop with 4 cores or a workstation with 4 cores. Of course, the speed up that you will see on your project depends on the hardware you have at hand and the kind of project that you have. So, and since Scala World is a very special conference, we thought we wanted to make it special as well. And we're going to give away 50% discount on all yearly licenses that are bought with the Scala World 2019 coupon. This coupon is valid 1 week, so in case you're interested, just go for it. Try it out. If you like what you see, just buy online. But over these years, what we found out is that Scala compilation is not the only drag. So it really comes from a realization of interacting with people, with developers, that when they think about Scala compilation, they might not actually mean just Scala compilation. And the reason is that we pretty much never compile Scala code using the Scala compiler directly. We interact with the Scala compiler through some other front end, right? And so basically, what we are benchmarking is not just raw Scala compilation, but it's Scala compilation through whatever front end we decided to use. And well, we might find out that that inefficiencies maybe are not just in the Scala compiler. Maybe it's not just the Scala compiler that is not fast, but there are other things around it that actually makes it look like as if it's slow. So in our ecosystem, SBT is the de facto build tool that we use to compile Scala code, right? More than 70% of the projects out there, according to the IntelliJ 2019 survey and also a compilation survey that we did last year, we see and we know that SBT projects are pretty much everywhere in the Scala ecosystem. And we all know that it takes quite a bit of time to get SBT to the point that is ready to compile. right? When you type SBT, you usually wait. You can't just start compiling. So that's definitely overread. And have you ever wondered about the difference on build times that you see on the CI and build times that you see locally? They differ many times, and it's not always clear why there is that difference, right? And last but not least, when you execute compile, when you execute test inside SBT, or any other task, well, that actually may trigger the execution of a multitude of other tasks, right? And those tasks can be fairly expensive. So the aim of this talk is really trying to take apart what inefficiencies are due to setup, so they're sort of caused by us, by the way we do things, from what is actually inherent and depends on SBT, on how SBT is done. So what's in an SBT build? Well, we can sort of picture an SBT build just as a collection of settings. These settings, they get loaded from different places. For instance, we add plugins in the global folder, and plugins have settings, right? So that's the first place where SBT looks at when it's loading the build. Then we have plugins defined also in our project folder, and plugins have settings. So that's a second place where SBT is going to look for settings. And third, even though it's maybe less, maybe it happens less often, but there is also settings that you might define in your build directly. So those are the three places where SBT is going to go, look, and load settings. So what is a setting? Well, essentially a setting generates a value. And to generate a value, a setting might use some other setting. So what we find out is that settings have dependencies. And you can really think about a setting when it gets evaluated as a function and that has argument. And the arguments of this function, well, are the dependencies of the settings, are the value of the settings dependencies, right? First, I need the dependencies of my settings in order to compute the value of my settings. So I can really picture that as a function. And the big question is, how can we find out about the dependencies of a setting? And the second question is, can we know from where they come, these settings? Can we know what plugin contributes these settings? Do you guys know? Do you know how to find out this in SBT? Perfect, yes. So in order to find out the dependency of a setting, we can just use the inspect command. So if I type inspect, if I'm inside the SBT shell and I type inspect3 and the settings name, well, that actually gives me a very nice printout where I can see exactly how is my setting computed and what it depends on. So in this case, we see that a source directory, so I want to see what are the dependencies of source directory, and I see it depends on base directory. And base directory itself is a setting that depends on this project. So those are the dependencies of the source directory. What about if I want to know where it's defined? Well, again, I can use inspect. This time I'm just going to drop the 3 argument. And if I call inspect and then the name of the setting, it's going to tell me exactly where that setting is defined. And well, source directory is a setting that is defined in SBT, so it shouldn't be surprising that the place where the definition, where it's defined, it's the actual SBT code. And defaults.scala is actually the place where, if there is an SBT setting, that's the place where you usually will find the implementation of that setting. So in our case, well, the source directory is defined as I'm using a base directory and I append the source string. So that's pretty easy and that's pretty clear. But have you ever wondered how many settings are there in a typical build? Would you be able to tell on your build, on your enterprise project, how many settings do you have defined? How many settings are loaded in your SBT build? 30,000. That's a really good number. So it turns out that I did a bit of experimentation. I went on a few open source projects. So the first 2 are actually play projects. They're all fairly sizable projects. And I wanted to have something that represents an enterprise project, so not a trivial one. And yeah, it was actually fairly surprised to find out that yes, 30,000 is the magic number. Projects out there, when you load the build, so when you just want to enter the SBT shell, there are about 30,000 settings that need to be loaded. And then we know that settings sort of divided into two. We have things that are of type setting type and things that are task. The setting type is something that needs to be evaluated before the build is loaded. So all setting values are actually being evaluated before I can start interacting with the build. So before getting into more details on settings, I wanted to give you, this is a digression. I wanted to give you, advertise actually, a little utility that exists in SBT that I find extremely useful for debugging my build. So how do you find out about how many settings you have in your build? Well, if you just type SBT and you look for the output, if you have more than 10,000 settings defining your build, SBT will tell you that. But let's say you have less. In that case, how can you find out how many settings you have in your build? Well, there is this little thing called the console project. It's just a task that is part of SBT. And the nice thing about it is that it gives you an interpreter, just a Scala rep, but with your build loaded in it. And that means that you can actually go and inspect your build. You can evaluate settings. So in order to know how many settings you have in your build, well, we can just take the build structure, which is basically the in-memory representation of your build. We call eval on it, which really has the same semantic as .value in your build files. It's just going to evaluate the setting. And with that, well, now I can actually query the state of the build and see how many settings do I have defined. So if I call settings.size on that value, I can see that actually the number of settings are the one reported by SBT. And I don't know, how many of you knew about console project? Good, yeah, I thought it was actually one of these things not many know about. And when you have a problem in your build, what do? Well, you might go and put some print line or similar things, and then you need to reload the build, so you have to wait. Then maybe what you did, I need some more print lines, so you add it, and then you reload again. And so you're actually wasting a lot of time. With console project, you can just go and do the side effect. You can actually even side effect your build. You can explore your build. It's just like exactly what you do with Scala, right? You don't know what this little method does on vector. You go on the interactive shell and you try it out. Do the same for SBT next time you have a problem, either with plugins or your build, and hopefully it will make you a lot more productive. But back to settings. So we have 30,000 settings. How do they get there? So what I did is that just created an empty project. How many settings do we have on an empty SBT project? So I didn't define anything on it. And I had no global plugins and no plugins in the project folder. Turns out I have 700 settings. 200 of them are global settings. 500 of them, roughly, are project settings. What does that mean? For every new module I'm going to add to my build, I'm suddenly having 500 more settings. So the more modules you have, the more settings SBT will have to load at start time. So that's one axe that sort of contributes to the explosion, but of course it's not it. So in our build, we have plugins that are contributed either from the global or the project folder. Well, those plugins have settings, and again, they're going to add to the explosion, right? And what's also interesting is that our so I don't know about if you know about all the scoping axes that we have in SBT, but we basically have 3 axes. Each setting can be scoped to 3 axes, and we can picture that as a 3D chart or a cube. We have the configuration axe, we have the task axe, and then we have the project or sub-project axe. So this is handy because, for instance, it allows us to use a unique setting like source directory and redefine its value depending on the context. So this is what we see here on the slide. If I'm compiling my application code, well, the folder is source main, right? But if I'm compiling my test code, then the folder is source test. If I didn't have let's say a way to scope the setting, then I would need to have two different settings. So that's actually quite neat, and it's very handy. However, maybe we don't need all those axes or dimensions, but that's for a different talk. But the other fact that is interesting, while it makes sense for source directory to have several axes, does it make sense for run? Have you ever run a test? No, you just execute the test. You want to execute the logic, but you run an application. You don't write your test. But run is also going to be scoped to test, not just compile. So there are some, let's say there are some way of scoping your settings by default that don't make a lot of sense. And this all adds up, basically. It all adds up and it all contributes to the explosion of settings that we have in our build. So finally, we understand how settings are, what settings are, and how they're treated by SBT. So we need to load those settings in SBT. So this giant collection of settings is going to be compiled into the task graph. And the task graph is going to make, it's there so that it makes explicit the dependencies between these settings. Once SBT is loaded, this task graph it will be used to execute your build, right? When you interact with it, you're effectively using the task graph. And we all know that loading the task graph takes quite a bit of time. In fact, I went ahead and did a bit of an experimentation, again, with the same projects as before, to see how much time does it take just to load the build. So the benchmark here is time SBT exit. I just want to see how much time does it take for me to load the build on different environments. Local is just really my local machine, where I've got everything cached. So you can imagine that scenario as being, I checked out the project, I did a full build, and then I'm benchmarking again. Right? So I've got everything is there, everything is cached, and we see it's always the fastest, right? Makes sense. Then I've got a CI with cache. So the CI with cache scenario is I'm caching the .iv2 directory so that all the artifacts, all the dependencies of those projects are there, are available. There is no downloading happening. And I'm also caching the .sbt folder, and I'll explain why just in the next slide. And last but not least, we have the CI without any caching. Let's say we're not really spending any time optimizing our build time. Well, that actually is going to cost us quite a bit. We see that the explosion in time is substantial. So what can we draw from here, from this? Well, one thing is that on the left, I also have the different SBT versions that these projects are using. One thing we can see is that the numbers, at least for local, they don't seem to be very much impacted on the SBT version. Of course, there are different projects, but I would say they're roughly equivalent. It takes about 15 seconds to load the build on these projects. And what we can see is that on the CI with the cache, it takes twice as much. Why is that? So I was mentioning the SBT directory. I don't know about you, but this was actually, that was a tweet from us about a year ago. We used drone CI for our build, and we were actually wondering, we got everything already, we thought we had everything already cached. We have a proxy as well, so that there's really no latency during resolution, we thought, to know whether the artifacts that the build needs are available or not. And despite that, it was still taking more than 100 seconds just to load the build. We were really clueless. We were really wondering, why is it taking so much? Well, it turns out that SBT, when it starts, there are quite a few dependencies that need to be downloaded by SBT in order to do its job. And where are those dependencies stored? Well, we only learned then that they're stored in the .sbt directory. So if you don't actually cache the .sbt directory, you're going to pay quite a bit on loading time just because those dependencies need to be fetched. But that's not it. There is more to it. Are you familiar with the compiler bridge? Who knows what the compiler bridge is? Okay, not a lot, like maybe a fourth. So the compiler bridge is essentially the interface that allows SBT to communicate with the Scala compiler. That's really what it is. For SBT, in order to call on the Scala compiler and compile your Scala files, it goes through this component that is called the compiler bridge. What's interesting is that the compiler bridge is actually shipped as a source component. The reason for that is that, so if you think about it, SBT interacts with the Scala compiler. So we know the Scala library is binary compatible, forward and backward binary compatible on minor releases, right? But there is no guarantee about the Scala compiler, the actual Scala compiler jar. In fact, the Scala compiler has, let's say, freedom to break whatever it wants. It's all sort of internal API. And that's why the compiler bridge is shipped as a source, because it needs to be compiled against the specific Scala version that you're using. And maybe you've noticed this message on the right, on your CI. It's telling you that it's compiling the compiler bridge for the specific version of Scala that your project uses. If you have multiple versions of Scala, it's going to do this for all the different versions that you're using. So it really makes a lot of sense to store the .sbt directory on your CI, because once this bridge is compiled, the binaries are actually stored inside the .sbt folder. And it takes about 10 seconds to compile a bridge. And the reason why it's a bit slower than usual is because the compiler bridge is usually the first thing that it gets to be compiled, because it happens during the build load, right? And so you have a call JVM, and so even if there are just a few files, it still takes quite a bit of time to compile that. Good. Another reason why you want to persist the .sbt directory, which is not on the slides, is because also the launcher jar is going to be downloaded once and then cached in there. So again, it's a small jar, but it's again one more reason to cache that directory. If you're using cached resolution, I don't know who's using cached resolution. Okay, the mini graphs that are sort of produced by SBT in order to be effective during resolution are cached inside the .sbt directory. So it's another reason to cache the full directory. Good, so now we understand the difference between the local times and the CI times. Locally, I don't have to read or load the I don't need to read or load the SBT dependencies, and I don't need to read or load also. I don't need to compile. No, sorry. Sorry. So we understand the difference between the CI with the cache and the CI without the cache, right? The CI with the cache, since I cache the Ivy directory and the boot directory, is doing a lot less than the CI when I'm not caching these things. And on top of that, the CI without caching these things is also downloading all the artifacts, and that's definitely taking a lot of time. So, yes?
Without the cache, it's 6 minutes for Ornicar.
Yes.
Is that because it's an older,
No, the reason is that it's a project that has a lot of dependencies. I don't think it's very much linked to the version of SBT. Maybe with 1.3.0, actually I'm pretty sure with 1.3.0 things are going to be better because SBT 1.3.0 is going to use a different, is going to use Coursier. But I'll actually talk about resolution and Ivy, so I'll just delay this a little bit more. But what about local versus CI times? Why is there a difference between these two? Right, and it is quite substantial, this difference. Have you ever wondered about this? Do you have the same problem on your CI? Have you ever spotted this on your CI? Okay. So yeah, someone suspected this to be I/O. Let's find out. So this is the output, let's say on the CI. Imagine I'm on the CI, SBT started. I highlighted the difference between the local development and the CI. So the log that we see there highlighted are the extra things that SBT is doing on the CI that is not doing locally. So what are these things? Well, updating means resolution. That's, when you say updating, that means SBT is resolving something. It's interesting because it's not actually really downloading anything. I got everything cached, But yeah, it's spending some time resolving. And then the second thing is it's actually compiling some Scala source file. The project I'm using for the output here is really not relevant. This is going to happen on your project as well. You might have less than 34 sources, but it's going to take some time. So I'm very happy to introduce you to the meta build project. This is why on the CI, it takes more time to load your build than on your local environment. So the meta build project is a synthetic project created by SBT to compile your SBT build. Your SBT build is written in Scala, right? That build has to be compiled. And how is SBT doing that? Well, by creating this, let's say, synthetic project whose job is to compile your SBT files. The meta build project has dependencies. What are the dependencies of the meta build project? The plugins that you might have in the project folder or in the global plugins, right? Those are all dependencies of your build. And resolution takes time. Even if you don't have to download anything, it still takes time for SBT to do resolution. And I'll talk about this very soon. So once the build file, once the meta build is compiled, well, the result of resolution together with the binaries of the build is stored in project target. So I didn't want to be controversial, but I think it would be interesting to, if you want to lower your CI times, it would be interesting to cache also the build binaries and the result of resolution. And maybe you should also cache the result of resolution, not just for the meta build, but also for the different modules that you have in your build. It's definitely going to make a difference. Of course, then it depends on how much time does it take your build to execute. So it might be relevant to save maybe 30 seconds or a minute, or it might actually make a huge difference. It really depends on how much time it takes your build, your full CI build to execute. So yeah, the best practices or the takeaways from this is really cache the .ib2 and SBT directory. Another thing that we have seen in the wild is some people calling SBT multiple times. I'd really recommend not to do that. Just chain the task or commands that you want to execute. And the reason is because you don't want to pay this loading time every time you're executing a task. You only want to pay it once, and then once the build is loaded, let's just execute all these different things we want to do on the CI. And last but not least, try to avoid snapshots. The reason is because of the way, well, the snapshots are, so there are these sort of dynamic versions. SBT has to go through all your resolvers to make sure that it's got the latest snapshot on the CI. So it's going to take time to actually go through each of the resolvers that you have defined in your build and to make sure that it's got the latest snapshot, right? If you must use a snapshot version of some dependency, at least I would say set up a local CI, a local proxy, so that you're not paying for the latency of the network. Or in alternative, you can bind a dependency to a specific resolver. And this is actually something I'm going to show you next. It's something we found out like maybe a couple of months ago that is possible to do. And it definitely helped bring in some sanity in our build when using snapshots. And I'll tell you a bit more soon. So even if I'm saying don't use snapshot, we actually ended up using it because we had no option. Another thing about SBT resolution with snapshots is that it might be surprising the way it behaves when you have a snapshot of a dependency but in local and cache. It's usually not going to do what you expect him to do, or it might do it sometimes, at other times not. So you're going to see things like, why was this working yesterday and not today? This problem is supposedly fixed in SBT 1.3.0. And the reason why it's fixed is not because they actually fixed the problem, but because they moved to a different dependency manager. But just making you aware of those little things that yeah, they can definitely hamper your productivity. You may just be gone on a quest of 2 days to find out that the problem was a bug on SPT with snapshots. So before moving on, the little thing I mentioned before with snapshot and sort of linking a dependency to a specific resolver. Did you know about these update options with module resolvers? No. Good. I'm glad. So here the thing was that when we were building on the so depending on the context in which we were building, we wanted a dependency to always be retrieved from a specific place. So on the CI, we wanted it to be retrieved always from the Maven cache. While when we were building on locally, then we were fine to actually get it from a remote repository. And these actually allowed us, this little utility allowed us to have this kind of behavior and sort of feel convinced that this was the way it was working. So it really, really helped bring insanity into our build. Before, we would just see spurious failures and really don't understand why it was happening. So if you can avoid using snapshots, otherwise this is a nice trick. All right, so we loaded the build, all good. We learned a few things about SBT that actually we can use to make the loading a bit faster. But what happens when we execute compile or test or even other task? It doesn't matter. I'm talking about compile because this is most likely the one that we use all days. But what I'm going to say, it's actually valid in general. So how can we know if triggering a task is expensive? It turns out that SBT ships with built-in profiling capabilities. And it definitely took me probably something like 5 or 6 years to find out that that existed. An alternative to enabling the SBT profiling capabilities is the SBT optimizer plugin. I'm not going to talk about this, but I would definitely encourage you to try it out. So how do you enable profiling? Well, with that little system property. You just start SBT with sbt.taskTimings equal true. And you'll see that the moment you load the build, the build is loaded, you will see a breakdown by task of what task was executed and what was the cost of that task. Very good. So I actually took again, I think this was the Guardian front-end project. So one of the projects I mentioned before, I said, okay, let's see what happens when I compile this common module after a clean. It's interesting because we can see that, well, compilation takes time. There are 520 source files. But the second one, the second task that actually takes the most is update. This is dependency resolution. What's maybe surprising is that it didn't have to download anything. This is just Ivy sort of figuring out what the heck does he have to do with the different dependencies and version and the conflicts, the potential conflicts, the exclusion rules, and everything else. It took 7 seconds. But I said, okay, well, we never clean, right? So maybe that's why it happened. So let's do it again. I didn't do anything. I didn't change anything in that project. I just compiled again. Well, again, update takes 1 second. And in this case, the update report was there. I didn't get rid of it. This was only deserializing the update report. And that was it. Like, it just deserialized the update report, which is a huge JSON file. And so this project has a lot of dependencies. So the JSON file that was produced, this update report, I think it was about 8 megabytes. So yeah, it wasn't small. So it definitely took some time. So why is resolution so slow? So I already gave you an intuition. And you probably heard this one a lot, like it's Ivy's fault. It is in some way, but not always. So in this case, for the update, why it takes so long, yes, it's mostly Ivy's fault. The reason why SBT decided to use Ivy was, well, because it was there. And it was also kind of cool at the time. So we didn't know that it didn't scale well. But it was kind of cool because it allowed you to have repositories with different schemas, or you could have a lot of flexibility with your repository, so you don't have to follow the Maven standard. So it felt very attractive. It's only later on that we found out that with the number of dependencies that we have in our projects, it really doesn't scale well. So really try to avoid doing clean, and the reason why you should avoid doing clean is not just because of the binaries, but mostly because of the update reports that gets deleted, especially if you have a lot of dependencies. It's going to take time to recreate that update report. It might make sense to create your own clean class files setting or task, so that you can just get rid of the bytecode while keeping the update reports. And a question that I've heard sometimes is setting up a proxy helpful for this problem? Or not? Well, it's not. So a proxy is very, very helpful for downloading dependencies, for basically avoiding the latency between you and the repositories. I would highly recommend you to run a proxy either on your laptop or within your organization, because it's going to make you resilient to the upstream repositories. If you have ever seen, if your build has ever failed because of a bad gateway, well, set up a proxy and you'll be good with it. So it still makes a lot of sense to have a proxy, but it will not help you with resolution time. And there I was just like writing what are the things that you need to do to set up to instruct SBT to use a proxy. You'll find documentation online. The point I wanted to make is that you need to start SBT with this SBT override repos equal true to make sure that resolvers that are added to your build are not going to circumvent the proxy settings that the proxy that you have set up and how you have modified the repositories file inside the .sbt directory. If you don't do that, then anyone in your team could add new resolvers and SBT will actually go through them. So it's good to know that, if you want to configure correctly the proxy, you also need to start SBT with that system property. So how to speed up resolution? Well, the easy solution is let's ditch Ivy, since it's actually responsible for most of it, and use something else. That something else, it's easily Coursier nowadays. It's really easy to try it out. You just need to add the SBT Coursier to your build. And that's great. The only thing you need to be aware is that Coursier has different semantic for resolving artifacts. So if it works out of the box, great, especially for handling conflicts resolution. So if it works out of the box, great. You don't have anything to do. If it doesn't, well, there might be a little bit of work to do, but I think it's really, really worth it. So if you can use a Coursier, it's definitely an option, I would say. If you cannot, and you're stuck with Ivy for whatever reason, then actually I have an announcement at the end, so just stay tuned for it. So, good. We know resolution. It's actually responsible for, a good slowdown, or it's partly responsible for long compile times, or it affects our compilation times. But are there any other tasks in SBT doing that? So this actually comes from a project in the wild. What they were doing is they were generating slick table definitions by connecting to a database. All right? They were connecting to the database, they would generate the table file, and then they would compile the project. Well, turns out they were doing this every time, regardless of whether there was any change in the database. They would just pay these 3 seconds, like their developers, every time they would type compile, they would have to wait 3 seconds, plus the time it takes to compile the Scala code. It's really bad. Do you know how to avoid it? Other than removing it and not generating the table, or actually generating it once and then making it part of your repository. That's definitely an option. But let's say you want to keep the same sort of semantic, but you only want to generate those tables when, let's say, migrations files have changed. Well, there is actually a little utility in SBT that is extremely useful for this. I was like, they just told me that it got documented. So if you go on the SBT documentation, there is quite nice documentation now about file function.cached. And the whole idea here is, okay, let's have some way to assess if my generation logic has to be run or not. And in this project, it was actually extremely easy. So at the end, so there was a folder with migrations files. If those migrations files were not changed, it meant the database was the same. It didn't change. And so there was no reason to regenerate the table definition. So here I'm really using this fact. I'm creating these function value cached generators, and I'm calling the file function.cached. The first argument is the store. So it's where do I want to basically persist the cache information. And the second one, it's an optional argument. So by default, this file function cached is going to use the file's timestamp. What I change here is, okay, instead of using the timestamp, I'm going to use the hash of the file. But in reality, I could have just used the timestamp. It was just to show you that there are actually different, this function is parameterized, and you can sort of adapt it to your use case. And what happens here is that if the migration files haven't changed, then the function body that is passed to cached is not going to be executed. And so those 3 seconds that we've seen before, well, we will not pay them. It will be just shaved off from our compile. Here is another one that I've seen fairly often. It's source formatting. So again, we tend to hook this up to our compile task because we want to make sure that before we push our sources or we open a pull request, everything is formatted well. I would say if you don't want to have the overhead, it might actually make sense to not have it hooked to the compile task. But even worse, with SBT Scala style, the plugin, if you look at the documentation, by default, it shows you how to set it up in a way that every time you type compile, it actually formats everything. It doesn't just format what you changed or the file that you touched. It actually goes and format the old project. And if you have a few sources, of course, that's not going to be a big cost. But the moment you have a lot of them, then it's really going to cost you some time. And again, maybe it's 10 seconds, but if you start adding 10 seconds here, 10 seconds there, it really adds up, especially if maybe your compile times are 20 seconds. So again, here I'm using file function cached. This time I'm using the default values. So when I pass the Scala source files to it, it's just using whether they were changed or not. And then inside there is a little bit of logic to understand whether there are new files that were added since last time I ran the formatting, or whether there have been files that have been removed. So I'm not going to go into details about how this works, but I thought it was useful to actually put it on slides. Then I'm actually going to share the slides on Twitter, so you guys can just copy paste in case this applies to you. Good. So the takeaway for me is really that there are things that depends on us. It depends on how we set up our build, and it's definitely worthwhile to think about how we are hooking up these different plugins or tasks into our build. And also when you execute things on the CI, think about whether you can, what can you cache, and maybe what you cannot cache. I mean, that's fine, but consider also caching the update reports or the build binaries, as it's all going to lead to smaller build times. And then there are actually inefficiencies that are inherent to SBT, and we've seen a couple of them. One is loading the build. I would like the build to be loaded just there, but we know it takes time. And IV resolution is another common SBT problem. So what can we do about those intrinsic problems that we've seen in SBT? So today, actually, I have quite an interesting announcement. So triple quote, we're going to expand our mission. Our mission was we wanted to own compilation time, and that's why we created Hydra. But since we felt that everyone is complaining about build times, we're going to expand our mission and own build times. So we're going to make Scala builds faster. And that means that we're going to start by tackling SPT. We want to have a fast SPT. That's the kind of experience that we want to deliver to you. So it has to be loading really, really fast. Resolution with Ivy should also be much better. And there are lots of other things that we can do. If there are things actually in your mind that you would like to see improved, just come and talk to me. I'll be really, really happy to hear your feedback about it. And also what you think about this. Good thing about open source is that just like Hydra, this will be freely available for open source. And after SBT, we're going to tackle other build tools. So if you're using Maven or Gradle, we didn't forget about you. And we're also going to do optimizations that are actually outside of the build tool. So even if you're using Bloop or maybe something else, we're actually going to make build times better regardless of how you compile or build your projects. Yes, if you're interested, just stay tuned. We start working on this and we expect to have something ready by the end of the year. So just follow us on Twitter. And yeah, thanks a lot for the attention and happy to take any question.